Hey again. I was thinking it would be good to get a little bit more practice under our belt while we're just learning the ropes with implicit differentiation. So I went ahead and turned the page. I'm on the top of page 2 now of Diff Packet 3, just to look at a few more examples with you. Check out the entire page. As you look over all of these functions, you don't see them solved explicitly for y. These are called implicit equations because you've got x's and y's throughout both sides of that equation. And in number 3, I'm thinking of what this graph would even possibly look like. I know that with a little bit of algebra, we could solve this thing for y. And we've got other options rather than using implicit. But if we don't have to, why take the time to do that algebra? Let's try this implicitly. I was looking at the graph too. Here's what the graph looks like. Definitely not your ordinary everyday function. But we want to take the whole derivative, both sides, with respect to x, d dx. And I thought this would be a good example because we've got a quotient rule situation on this left-hand side. I'll put QR for quotient rule. And that's what we're going to dive right into. So I got to set up a quotient rule on the left-hand side. We'll take derivative of the top for starters. So derivative of just x with respect to x should be 1. That gets multiplied by what we see in the denominator, x plus y. Okay. Then minus, we're in the middle of a quotient rule here. We got to reverse it and take the derivative of the bottom. So x plus y here, derivative of x we said is 1. Derivative of y with respect to x, right, should be 1, but then chain rule it on with implicit. This is a y term, a dy dx. So this should handle, what's in parentheses here is the derivative of the denominator. And that gets multiplied by the numerator, so just times x. I think we have all parts that we needed of that numerator of the quotient rule. On the bottom, I won't forget, I take the original denominator and it gets squared. That's our left side. Right side doesn't look as bad. I've got all easy to handle terms that are in terms of x. So you've got the derivative of 3x squared, a 6x, and then minus the derivative of 6x itself, which is just 6. And then remember our next goal. Okay, so we look at what we just wrote. And we have the task of getting the dy dx all by itself on one side of the equal sign. Now, luckily, there's only one of them, but unluckily, man, it is trapped. It is entrapped inside of parentheses on the top of a quotient. We need to do some simplifying. So let's get rid of that denominator on the left-hand side. Let's multiply both sides by this denominator. So simplifying the numerator, you have x plus y. You have, let's distribute this x into the parentheses. So we've got minus x, that'll be good to get something to cancel, and then this negative, so minus x that gets distributed times dy dx. And then what we had said we were going to do originally was multiply this over to the other side, so we have no denominator on the left side, and you'll have 6x minus 6, that was already there, multiplied by x plus y squared. We're getting a little closer to getting dy dx by itself. Looking at the left side, something we said was nice was these two x's, x plus x minus x, those are additive inverses, and we just have to work on getting other terms over to the right-hand side. Let's subtract y over to the right. I'll move this up a little bit. So if we move the y over, all we have left on the left side should be negative x times dy dx. And on the right, we have what was already there, minus a y. So I could just write a negative y out front. Negative y plus, let's say, what was already there. So 6x plus 6. And I shouldn't change that to a plus. That's a classic Wesley mistake. Let's keep that a minus. And then what else was there? X plus y squared. Okay, last but not least, to get x dy dx fully isolated, we need to divide both sides by negative x. So there's a couple ways we could show this final answer. We could put the whole thing over a negative x, or we could put the whole thing over a positive x as long as we change these two signs up top. So as long as we make it positive y, which is nice because that's more positives than we used to have. And then this could become a minus. And then here goes what's in parentheses. And that what I think I'm going to leave in parentheses too. 6x minus 6, and then x plus y squared. And like I said, for now, that's as far as I'm going to go. We have this as an expression for the slope of the tangent line. If we had a y and an x, we could plug them in there, but that looks okay for now. I had a few more I picked out that I thought would be good. All this is good practice. Can you flip the page to page 3? There were two that I was looking at specifically. There's a couple trickier ones on this page that involve chain rule, and we haven't really seen chain rule mixed with implicit yet. So I wanted to try either 11, 12, or 13 with you. I'm thinking I'm going to try 12. And it's got this first term that needs to be focused on, and it's got an e to the xy. It's e to a product, so this is really going to involve an outer and inner part of a function, so definitely chain rule. And also I'll put PR for product rule because you do have that xy in there. So maybe this one should get a star. So that's the first thing we're going to do. Same directions on this page. We have an implicit equation that doesn't have y by itself, so a good option would be to take the derivative with respect to x of both sides and use implicit. And remember, every time we differentiate a y term, we're going to tag on that dy dx. So let's see what we have. E to the xy. Well, the main event, right, the outer part of the function is that you're raising e to something. And e to the something is its own derivative. We're going to say that's got a derivative of e to the xy. Okay, so we've handled kind of like e being raised to a power. Then let's chain on an inside derivative that's going to involve, like we said, a product rule. So we've got what? U prime v plus v prime u. Derivative of x times y normal. No need to use a dy dx. We didn't take a derivative in terms of y. And then plus, let's say regular x times y's derivative. So y's derivative is going to be 1. And then the derivative of y with respect to x. Here's where a dy dx gets tagged on. And now this, everything I wrote in black here, I'll switch colors now to blue, but everything I wrote in black was handling that very first term. And then I think we get a little bit of relief with the other terms. Plus x squared, so just a normal power rule derivative, minus y squared, so normal power rule derivative, but it is a y term, so take an inside derivative dy dx. And then I don't want to forget to differentiate the other side of the equation, the 10, derivative of 10 with respect to x is going to be 0. So a little bit more to think about and a little bit more work still to be done with getting the dy dx by itself. But it's so funny how now the algebra is just the part to be really careful with. Generally, you got a dy dx inside here that's trapped. You are going to want to get rid of the parentheses. So we can distribute in to do that and make this y times e to the xy plus, here it comes to the next term. How about x times e to the xy with dy dx? Okay, so there's one dy dx. Then you have all the rest. I'll just recopy. Plus 2x minus 2y dy dx. And our focus is now going to shift to getting the dy dx's on the same side, which they are, moving everything else over to the other side, and GCFing to try to get dy dx by itself. So these two terms are going to stay on the left. They both have dy dx's. So I'm going to GCF out a dy dx, and in parentheses have their coefficients. So x e to the xy, and then minus 2y, I believe, should do it. What does it equal? Well, here are these terms which get subtracted over to the other side. So negative y e to the xy, and then minus 2x. You're going to start to see a rhythm with these questions. Moving the dy dx's to the same side, followed by a GCF of dy dx, and then a division step, right? To finish this out, truly getting dy dx by itself, we can make a fraction. And it would have this numerator, negative y e to the xy, and then minus 2x. All over x e to the xy, and then minus 2y. We'll leave that. That's your expression for rate of change. I was thinking about this function and what it might look like too, so I checked it out on Desmos. The original graph is going to look like this in blue here, kind of a cool shape. And now the answer we got is a good expression for the rate of change. A lot of these, I want you to look back at all these for good practice, but the other one that caught my eye, I was looking at the bottom two because they both had natural logs. So I want to close things off maybe with 16 and just try to go through the terms. Same idea, right? It's not conveniently solved for y. Implicit's a really good option here. And we have to just kind of really focus on that first term to make sure we handle the chain rule part of it. And then I notice Probably going to have a product rule part of it too, with that xy being a product in there. So give it a try. 16, let's see. We have to take a derivative with respect to x. Start with the main event that you're taking the natural log of something. So you got to think back. Derivative of natural log of something is 1 over that something, right? Derivative of natural log of x is just going to be 1 over x. So here we have natural log of xy. Let's make its derivative 1 over that xy. As long as we tag on an inside derivative, being mindful it's a derivative with respect to x. So what? Derivative of x is a 1 times y normal plus regular x, gets recopied, times y's derivative, which is a 1, but then a dy dx. We've seen this before. Okay. And then let's see, we have a 5x, so its derivative's got to be 5, and we have a 30 on the other side. Doesn't really matter to the derivative. Any constant over there would have given us 0. Okay, so at least we only have 1 dy dx this time. It is trapped in parentheses, so again, my advice would be to get rid of those parentheses, distribute through. So we've got this into that, so the y should cancel here, and you get a 1 over x with that first distribution. And then what, 1 over xy into this term? So x's should cancel. You'd have plus 1 over y, dy dx, I believe. And then plus the 5 equals 0. Get everything that doesn't involve a dy dx to the other side of the equation so that we can solve easily for dy dx. So I'm going to leave this term on the left. 1 over y, dy dx. You have to admit this is kind of fun, no? And then we're going to move the 5 and move the 1 over x. So subtract both of those guys over. Negative 1 over x minus 5 equals that expression. Last but not least, we can multiply both sides by y to get rid of the fraction on the left side. So you have dy dx now equals y times both of these terms. So y times negative 1 over x minus 5. And you can feel free to leave it like this. If you don't love the parentheses in your final answer, you can distribute in the y. And I think we've got it. Yet another derivative that is in terms of both the variables x and y. All right, enjoy your day. I will talk to you soon, and happy practicing.